In addition to the transformer using power system, another application for transformers is for the impedance matching and or change the impedance. Let's see. Here I have the ideal transformer, and there let's see I have N1 turns on the primary winding and N2 turns for the secondary winding, and I have a resistance R connected to the secondary side, right? And let's see find the equivalent impedance R in. So the R in, without any doubt, that should be equal V1 over I1, right? And then we need to find out what's V1 and I1. And based on the voltage ratio, and because it's both from the dotted to undotted, so we don't have a negative sign for the voltage ratio. Remember, voltage ratio, they are proportional to, voltage ratio is proportional to the turns ratio, which is N1 over N2. And the current now, since both going into the dotted terminal, that means their flux add up, right? Because the permeability is infinity, so therefore the I1 over I2 is equal to negative N2 over N1. They will always be proportional to the inverse of the Laplace transform, the inverse turn ratio. And let's see, from this one we get V1 is equal to N1 over N2 times V2, right? And from this one we get I1 is equal N2 over N1, don't forget about this negative sign here, times I2, right? And also V2 and I2, they are not following passive sign convention with respect to the resistance, right? So therefore V2 over I2, we also know that should be equal negative R, because they are not following the passive sign convention. So with these three, I think we're ready to find out this one here. So the R in is going to be equal to V1 over I1, that's just equal to this one over this one, right? So we have N1 over N2, and we take the square, and V2 over V1 is negative R, so we have negative sign there, so that's just equal to R. So therefore the equivalent input resistance is going to be equal to the N1 square over N2 square times R. And so this is proportional to turns ratio square. That means if your turns ratio is, let's see, is 2, and then the input resistance is going to be 4 times, right? Because 2 squared, right? So let's look at an example and see if this will also get all the turns ratio for the transformers all together. So let's see. So we have the source. So in this circuit given in phasor, I should mention that all the voltage ratio, the current ratio, and also the equivalent impedance, they all hold for the phasors, for the S domain. All should be fine. And let's see with this circuit with the phasor, and also this phasor, really the voltage has 0 phase angle, really is a real number, right? So almost the same as DC, but the conceptually the VT is sinusoidal. I don't really know what the frequency is. That's the amplitude of that sinusoidal voltage. Maybe frequency very high or very low. I don't really know because it's not a given, and it's not really relevant to the question the problem we're trying to solve. So let's see, find the turns ratio. We know this one, the load resistance, and we know the RT. Think about the Thevenin equivalent resistance, and we are trying to find the turns ratio that can maximize the average power delivered to the load. So if you remember the impedance, when we deliver the maximum amount of power, now we only have a resistance, right? And we need to match the resistance with this the resistance the RT. So let's see, I have the R equivalent resistance, and this REQ should be equal to RT to deliver the maximum average power, right? So therefore the REQ should be equal RT, which is equal 50 ohms. And also we know REQ is equal to N1 over N2 square times RL, right? So therefore RL is known, REQ also known now, and therefore we can figure out what's this N1 over N2. So N1 over N2, that's going to be equal to, if I divide R sub L on both sides, and we're going to have REQ over RL, and I take the square root. And that will give me, I calculate the numbers, so that should be 0.316. Although this is decimal, but you can have the different number terms to getting close to this, right? So this is the ratio between the N1 and N2. And let's see the IS. IS actually is fairly easy. Once we find IS is going to be equal to VT over RT times REQ. RT and REQ both known, they actually are equal. Actually, that's going to be 200 divided by 50 times plus 50. And we got equal to 2. The phase angle 0. This should be amps. And what would be the load current? And let's see the load current I sub L. Right, I sub L. This one here, let's do the current ratio first, and in 2 steps. So the current ratio, since one is going into dot terminal, the one is leaving from dot terminal, so therefore they are going to be proportional to the inverse of turn ratio without this negative sign, right? So we have IS over I sub L. That should be equal N2 over N1 without the negative sign, right? So therefore, based on these, I can get I sub L is going to be equal N1 over N2 times I sub S. Everything is known, right? The turn ratio is we solved that, and we solved the IS, so everything is known, and the actual number is 0.632, and the phase angle 0, and this many amps. Okay, so that's the simple example for the ideal transformers. And also in the Google Colab notes, I tried to get the maximum power, and you can check the Google Colab notes, the code, and there's a plot for the actual power delivered to the load, and we can see that this turn ratio actually gave us the maximum power delivered to the load. Okay, so that's the 3 video clips we're gonna have for this lecture. And remember, no matter what you do, you just need to keep going and never stop. See you next time.